Hello, everybody. My name is Xueming Lin. So I will one of the team member to present this tutorial. The whole team consists of Professor Yixia Fang, Professor Dr. Kai Wang, and myself, and Wenjie Zhang. Here's the organization of this tutorial. I will present introduction using 10 to 15 minutes. Then Dr. Kai Wang will present the works on peptide networks for 20 to 25 minutes. And Professor Fang will present works on other general HRINS. Okay, also using 20 to 25 minutes. Professor Wenjie Zhang will present related work and future works by 20 to 25 minutes. First, I will give HRIN examples. So there are two types. There are two types of HRINS. The first is a special type, is on peptide graph. So a peptide network consists of two layers of vertices, top layer and the bottom layer. In eBay, customer data typically is a peptide network. So we have the top layer customers and the bottom layer products. There are other general HRINS which consists of multiple types of vertices and multiple types of edges. DVLP network, online movie database, IBM knowledge base data, and Twitter. So these are typical general HRINS. In this talk, we basically will focus on cohesive subgraph search. So this is a very fundamental research topic in network size and has been studied over 50 years with thousands of papers. So it's actually this actually can support a wide range of rare applications. Most existing works focus on homogeneous networks. So the models and the algorithms cannot be applied to HRINS. We need to develop new models and algorithms for HRINS. The main challenges are multiple types, huge data size, and dynamic data. So later in this tutorial, my colleagues will address these issues. There are many applications of cohesive subgraphs on HRINS. Fraud detection, group recommendation, heterogeneous entity detections, community search, network modeling and analysis, network visualization, and team formation. So I will address some of them in my talk. The first one is about user item network. So we want to detecting click farming actions in Taobao and other e-shopping platform. People from time to time, people want to do click farming. So this is actually not something new, right? We have a long history of click farming. Okay, so this is what people will do. They click a product. So this action will be recorded. So if you put a product into your shopping list or you purchase it, that'll be recorded. And then when you ranking products, it's based on the popularity among the users. So if you click more, the items will be ranked higher. This is actually the reason why we have click farming. And the challenge is in such applications, there are huge data. So we have billions of buys and products, and we have 10 plus billions of transactions and dynamic data. And we need, we need to compute we need to figure out such click farming, as quick as possible, right? Okay, so actually a very popular method is to compute bipeptide, by click on bipeptide graphs. Okay, so for the previous application, we actually have collaborated with Alibaba, and we put the software online in the last couple of years. So the result is very good. So we can because the computing power, right? Because the computing power is getting much better, so the efficiency can be increased about 40–50%. So the next one is about group recommendation. So we usually want to do the group recommendation among the customers. So here's one example: user movie network, right? So we want to detect alpha beta call. So this is so-called alpha beta call. In unipopulated graph, we could have k-call, so on so forth. But in bipeptide graph, we need to have degree constraints on both sides. So one is alpha, the other is beta. This is also an application of bipeptide graph. Okay, so we want to analyze heterogeneous genomic scale data by enumerating maximum by click. So here's the scenario: we compute a bipeptide graph. We compute by click. Then with the by click, we form a deck. We form a deck for further analysis. HINS analysis can also be used in network visualization. So we know visualization basically want to convey the clear ideas to the users. So in this case, the left-hand side is a network. So we want to do the projection, right? Say in this case, for instance, we want to do the projection on users. Then with the right-hand side, we actually calculated two critical nodes, Ruth and Opel. So these two nodes are actually the bridging nodes. So if you remove those two nodes, the network will be divided into two parts, right? So if you use the computation on HINS, we can come up with this, right? Finally, we can see the applications on DBLP networks. So we can, in DBLP networks, typically there are different types of nodes. Like in this case, the core number equals 3, core number equals 4, core number equals 5, and so on and so forth, and different ages. So we can we can display those different types of edges and the nodes, right? By the calculation, firstly by the calculation, and then we use different colors to to display them. Right. So what we'll cover in this tutorial, we'll cover call, we'll cover trust, we'll cover click, we'll cover connectivity. We will cover we'll cover connectivity-based cohesive subgraph. We'll cover density-based subgraph and others. Okay, so I will pass this talk to my colleague, Dr. Kai Wang.
Hello everyone, thanks for joining our tutorial. My name is Kai Wang. In this part, I will present works on bipeptide networks. Here is the outline of my presentation. So firstly, I will introduce basic notations of bipeptide networks. And then I will introduce the cohesive subgraph models on bipeptide networks, including call-like, trust-like, click-like, and density connectivity-based models. Here we use G to denote a bipeptide network, or say a bipeptide graph, which consists of a vertex set denoted as V and an edge set denoted as E. Note that the vertex set can be further participated into two different vertex layers, which is denoted as U and L, and the edges can only exist between two different layer vertices. As shown in this table, we classify the cohesive subgraph models on bipeptide networks into 5 categories, and I will introduce each of the categories one by one. Firstly, I will introduce call-like models. The first model I would like to introduce is called the fractional key-call, which is originally designed to handle author paper networks. Generally speaking, it projects the bipeptide network into a weighted unipeptide network of authors, and which is a co-authorship network. And the weight between two authors can be computed using this function. Here, X and S prime denotes two authors, and Y denotes the papers they have co-authored. So WE is the weight of the edge between these two authors. So according to this function, the weights between two authors are highly affected by the number of papers they have co-authored, and two authors have an edge if they have co-authored in at least one paper. And defining weights like this can ensure that the sum of all weights is the number of papers. Using such model, we can adapt the key-call decomposition algorithm for this weighted network to detect the hierarchy of the authors, and also we can find the dense regions if we apply the key-call algorithm. However, such projection method often suffers from two major drawbacks. Firstly, it will cause edge explosion, which means the number of edges of the projected graph can be much larger than that of the original graph. Also, it can cause ambiguous because of the information loss of one entire vertex layer. To avoid such graph projection, the generalized two-mode call is proposed on bipeptide graph by directly extending the key-call model. A generalized two-mode call is a subset of nodes C, which is denoted as call PQFG. Here, PQ are two integers and are two thresholds, and here FG are two functions defined on the vertices. And we require that for all the upper layer vertices in C, Fu larger than or equal to P. And we also require all the vertices in the lower layer of C, GV larger than or equal to Q. And also we require the maximumability. Here are some examples of the functions. So basically, we can use the degree of a node within C. And also, we can use the input degree, the output degree, or in a directed network, we can use the sum of widths of links. Specifically, by using the degree function, the alphabetical model is further investigated. So the alphabetical is the maximal subgraph in which each upper or lower layer vertex has at least alpha or beta neighbors in the subgraph. And here is an example of the 1-3 call. This is because for each upper layer vertex, they have at least one neighbor, and for the lower layer vertices, they have at least three neighbors. The intuition behind the alphabetical model is that, comparing with the traditional K-call model, the vertex degree onto different vertex layers can be much different. So we need to use different thresholds for different layers. To efficiently retrieve the alphabeticals, in the literature, an index called the Bicol index is proposed, which can support optimal retrieval of the vertices of any alphabetical, and the space complexity is only OM. This index is actually designed based on the nested structure of the alphabetical, which means that for a alphabetical, it is always a subgraph of the alpha beta minus 1 call, and it is always a subgraph of the alpha minus 1 beta call. According to such property, we can organize the alphabetical calls in a hierarchical way. Here we give an example of how to query the alphabetical based on the Bicol index. Suppose we want to retrieve the 1-3 call. Firstly, we go to the index IU and find the node block 1-3 and 1-5 and return the vertices U5, U1, U2, U3, U4, and U6. And then we need to go to the index IV to find the node block pointed by 3-1. And then we will find three lower layer vertices V5, V3, and V4. Based on the alphabetical model, the alphabetical community model is further defined by requiring the connectivity. Because the original alphabetical definition does not require connectivity, so which will group two disconnected groups into one alphabetical. By further requiring the connectivity, we can solve this issue and can use the alphabetical model to do community search. However, the alphabetical and the alphabetical community model only ensure the structure cohesiveness, while overlook the edge weight in forming the community, which is also a very important factor. For example, in this user movie network, each edge has a weight denoting the rating of a user to a movie. So if we apply the alphabetical community model to search a community of Herrick, we'll find this subgraph. And we can see it will include the movie Alien, which is not liked by Andy and Ken. And also, it will include the user Taylor, which has low ratings to 3 movies in this category, which means that she may not interest in such genre of movies. So the significant alphabet community model is proposed by further considering the edge weight on Bapt graphs. So we have defined the bipolar graph weight as the minimum edge weight in a graph G, and the significant alpha-beta community model requires the connectivity and the cohesiveness and also the maximality, which means it has the maximal weight among all the alpha-beta cores. For example, in the right example, we can see the subgraph in blue color is the significant 3-2 community, which excludes Allen and Taylor. By applying the significant alpha-beta community model on real-world graphs, we can see here is a user moving network. The result returned by alpha-beta core model contains several low-rating edges, but the significant alpha-beta community model contains a more cohesive group, which means that if we use such result to do personalized recommendation, we have higher probability to find the community of the query user. Here we introduce another core-like model called strengthened alpha-beta core. The motivation is that alpha-beta core assumes the equal importance of edges, so it will blindly include both loosely connected regions and dense regions. And the state-of-the-art method to model tie strengths is to use the butterfly support number. So a butterfly is a 2x2 biclics on bipolar graphs, and the butterfly support number is the number of butterflies containing an edge. By using such concepts, we can define the strong tie as given a strength level tau. An edge is a strong tie if it is contained in at least tau butterflies. And also, we can define the vertex engagement as the number of strong ties of a vertex. So the tau-strengthened alpha-beta core can be defined by replacing the degree of the vertex as the engagement of a vertex. For example, in the right figure, the whole graph is a 2-2 core. By using the tau-strengthened model, we can exclude the relative sparse region containing 3 vertices U0, V0, and V1. In the next pages, I will introduce truss-like models. The truss-like model is usually defined based on the butterfly structure, which, as I told before, is a 2x2 biclic. So K by truss is the cohesive subgraph where each edge is contained in at least K number of butterflies. And consequently, the bi-truss number of an edge E is defined as the largest K such that a K by truss contains E. So in the literature, many researchers focus on the bi-truss decomposition problem, which is to compute the bi-truss number for each edge in G. For example, in this example, the edge U0, V0 has a bi-truss number of 2. This is because they can be contained in a subgraph where each edge has a bi-truss number of 2. Different from the K-by-truss model, the K-tip is proposed by imposing the butterfly constraint on each vertex. It requires each vertex is contained in at least K butterflies. In addition, the butterfly connectivity is required, where each vertex pair is connected by a series of butterflies. And also, the K-tip number of a vertex is the largest T such that there exists a T-tip containing a vertex. So tip decomposition also aims to find the tip number of all the vertices. And the main idea of tip decomposition is similar as the peeling algorithm of K-core or K-truss. Firstly, it's counting how many butterflies each vertex participates in, and then it iteratively assigns tip number in a non-decreasing order. For example, this subgraph is a two-tip. Another trust-like model called quasi-trust is defined on bipedal graphs based on the concept of special edge. If two vertices from the same layer share some common neighbors, then a special edge is added into the bipedal graph. For example, in this figure, because H and I share common neighbors V1, V2, and V3, so there is a special edge denoted as dotted line is added into the bipedal graph. So with more triangles sharing a unique special edge, a dense subgraph in G is expected to be identified. After, after that, we can identify the maximum quasi-trust, in which is the subgraph in which a special edge is contained in the maximal number of triangles. So after obtaining the quasi-trust, we can remove these special edges, which result in dense subgraphs in the original bipedal graphs. Next, I will introduce the clique-like models. On bipedal graph, the biclique is a complete bipedal graph, and a biclique is called a maximal biclique if it is not contained by any other bicliques. Beyond this, we also have the definition of maximum edge, maximum vertex, and maximum balanced biclique. For example, in this figure, this subgraph is the maximum edge biclique because it contains the maximum number of vertices. It is also the maximum balanced biclique because it contains the maximum number of equal vertices in two different vertex layers. And also, this biclique is the maximum vertex biclique because it contains the maximum number of vertices. So in the literature, the maximal biclique enumeration problem is well studied. It aims to find all the maximal bicliques. Note that the outputs of maximal biclique enumeration will give us the result of maximum edge, maximum vertex, and maximum balanced biclique, and it is a NP-hard problem. If we want to directly find the maximum vertex biclique, it is not a NP-hard problem. It can be solved in polynomial time. And if we want to find the maximum edge or the maximum balance biclique, they are both NP-hard. But we can design further pruning rules to accelerate the computation process. To enumerate all the maximal bicliques, the branch and bound framework is usually used. So we maintain a partial biclique and recursively add vertices into it and check maximality. So, for example, in this figure, from the root node, we can directly add vertices to the partial biclique, and if there is a non-maximal biclique, we just stop the iteration. Besides the definition of biclique, we also have quasi-biclique. A quasi-biclique is almost a biclique in the sense that we are allowing it to miss a certain number of edges. For example, here is the example of gamma quasi-biclique, which is defined based on the connectivity and density. And we also have the epsilon quasi-biclique. So the epsilon quasi-biclique is defined based on the degree. We can see the definition. The vertex set is epsilon close to being a biclique if every vertex in the vertex set is adjacent to at least 1 minus epsilon portions of the vertex set in the opposite layer. So we also have other models including the alpha quasi-biclique, the error-tolerant epsilon quasi-biclique. Next, I will introduce the density and connectivity-based models. There are several metrics to define the bipedal graph density. For example, For given a bubble graph G, for any induced subgraph ST, we can define the density like this. We can use the number of edges divided by the square root of the number of the vertices. So this example, if we compute using such metric, can compute this density. So another way to define density is using the number of edges divided by the number of vertices. So if we compute the density using this metric, we will have a different result. Another way to define density is based on the concept of PQ biclic. Given a vector graph G and two integers P and Q, its PQ biclic density is defined as the CPQG divided by the number of vertices, where CPQG is the number of PQ biclics in the G, and a PQ biclic is a biclic consists of exactly P upper vertices and Q lower vertices. So we also have the concept of PQ biclic density subgraph, which is the subgraph has the highest PQ biclic density among all the possible subgraphs. For example, in this figure, if P and Q are set to 2, then the 2G biclic density in the network is this subgraph. The difference between the PQ biclic density and previous density metric is that it can be adjusted by adjusting the parameter P and Q. Consider the connectivity. We have the definition of k-neighbor graph. Given a bubble graph G, the k-neighbor graph GK is defined on the upper layer, which can also be defined on lower layer. So if two vertices has an edge, if they share at least k neighbors in the original graph G. For example, below is the two neighbor graph and three neighbor graphs of G. We can see U1 and U2 has edges in the two neighbor graph, but does not has edges in the three neighbor graph, which means that they has two common neighbors in the original graph. So this concept is also based on the graph projection, similar as the fractional K-call. Now is the conclusion of this part. We have introduced different groups of cohesive subgraph models. The cohesiveness constraints are formulated differently for this group of models. For example, they can use degree, use butterfly to formulate different cohesive constraints. And also, in the first three groups, most of the model have the nested property. And like the unipartite network cases, there exists a trade-off between the computational cost and structure cohesiveness for these models. For example, the core-like model are usually can be simply computed, and the clique-like models are usually hard to compute. That's all for my presentation. Thank you for listening. You can ask me if you have any questions.
Hello everyone, my name is Yi Xiang. I'm an associate professor in the Chinese University of Hong Kong, Shenzhen. I'm going to present the existing works about cohesive subgraph search or other general heterogeneous information networks. Here is the outline. I will mainly introduce four groups of works, which are core-based, chance-based, clique-based, and density-based models and solutions. I will also introduce a few other models and solutions. The specific work in each group can be found in this table. You can also find it from our tutorial paper. First, let me introduce the core-based models. The first one is called KP-core model. Let us see the motivation. Suppose we have a DPLP network which consists of 6 authors, 6 papers, 1 venue, and 2 research topics. For example, this edge means that the author A1 writes a paper P1, which is published in the venue V1, and it also mentions the topic T1. Then a natural question is how to find a community of researchers in the DBLP network. So we focus on the community of the vertices with the same type. Usually a community needs to satisfy two criteria. The first one is called connectivity. To do this, the authors use a metapath to establish the relationship between two vertices. For example, this is a metapath APA, which describes the co-authorship between two authors. The second criteria is called engagement. The authors adopted the KPK model, which requires that each vertex is connected to at least k other vertices in the community. Based on the discussions above, the authors propose the basic KPK model, which is a set of vertices such that each vertex is linked to at least k other vertices, while k instance of the metapath. However, it suffers from the issues of weak engagement. For example, by using the metapath APA, we can induce a homogeneous graph like this. You can see that, for example, A5 is connected to 3 authors, which are A2, A3, and A4, while 3 different metapaths. You can see there are 3 metapaths. However, these 3 metapaths share the same age between A5 and P5. This means that if this age is removed or wrongly collected, then A5 will be isolated from the community. This issue will be even more serious when the metapath is longer. To tackle this issue, the authors propose the age-disjoint and vertex-disjoint KPK models such that the K metapaths do not share any edges or vertices. Based on the 3 KPK models, the authors introduced the problem of community search over large heterogeneous information networks. The problem is defined as follows. Given an HNG, a equivertex Q, and a symmetric metapath P, which connects the vertex type of the equivertex Q, an integer k, and a specific KPK model, then the goal is to find the corresponding KPK containing the equivertex Q. Here is an example. Suppose the equivertex is A1. The metapath is APA, which describes the co-authorship between two authors, and k equals to 3. If we use the basic KPK model, we will find a community of 5 researchers, which are A1, A2, A3, A4, and 5. However, if we use the age-disjoint KPK model, then we will find a community of 4 researchers. Please note that A5 is excluded from the community, so you can see that the community of the age-disjoint KPK model is more cohesive. To find the communities, both efficient online algorithms and index-based algorithms are developed. The online algorithms follow a peering-based paradigm, which iteratively removes the vertex that participate in the minimum number of metapaths, while the index-based algorithm first decomposes the graph into some cores and then organize the cores in the tree structures. After that, when the query comes, it uses the indexes to search the specific core containing the query vertex. Next, let me introduce the relational community model, which is also called RCOM model. This model is designed for modeling a community of vertices with multiple types. Here is the motivating example. Suppose we have a DBLP network. There are some authors, some papers, some venues. Then the goal is to find a community of researchers and papers. To do this, we may need to specify some constraints. For example, each author publishes more than 2 papers. Each paper has more than 3 authors. Such kind of constraints can be modeled as relational constraints. Each relational constraint is a triplet. For example, this is a constraint, which means that each also publishes at least 2 papers. So to find such a community, we need to specify a list of such constraints, which is also called the community schema. Based on the discussions above, the relational community model is formally defined as follows. First, it needs to satisfy the constraint of connectivity. Second, every vertex satisfies all the relational constraints, which is also called the schema. A relational constraint is a triplet, L1, L2, K, which means that each vertex with label with vertex type L1 must have at least K neighbors with label L2. So you can see that this constraint is actually extended from the classical K-core model. Based on the R-core model, the authors studied the first problem, which is defined as follows. Given an HN and a schema, then the goal is to find all the maximal relational communities. To find such communities, the algorithm is very simple because we just need to iteratively remove vertices that violate any constraint in S and try to avoid repeated scanning of vertices. They also studied another problem which aims to find the minimum community containing the critical vertex. Since this problem is NP-hard and it is also NP-hard to approximate, they also proposed some greedy algorithms by using greedy local search. We ignore the details due to the time limitation. Next, we introduce the K-coherent core model. This model focuses on the multi-layer network, which consists of multiple layers. For different layers, they share the same set of vertices, but they share different sets of edges. This model is also called KCC. It is defined as follows. In a multi-layer network, a subset of layers and an integer k, the KCC is a set of vertices such that they form a K-core in each layer. So basically, it is a cohesive subgraph in each layer. Let's see an example. Suppose this is a 3-layer network, and each layer is a single graph. So you can see that the vertices A2, A3, A4, and A5 form a 2CC, because in each layer, these 4 vertices form a 2-core. For example, in the first layer, A2, A3, A4, A5 forms a 2-core because each of them has at least 2 neighbors. Similarly, these 4 vertices form a 2-core in the second layer and also in the third layer. So that's why these 4 vertices form a 2CC in the 3-layer network. Based on this core model, the top edge diversified coherent core problem is studied. This problem aims to find a set of edge vertices such that each SI is a KCC of a multiple layer network and the coverage of S is maximized. Here the coverage is defined as the union of all the vertices in the edge sets. This problem is NP-hard and they also propose some efficient approximation algorithms. We ignore the details here, but they can be found from these 2 research papers. The last core model is called A1, A2, AK core, which is defined on the K-pattern network. Conceptually, a K-pattern network is a network with K disjoint sets of vertices, such that for vertices from the same pattern, they are not connected, while for vertices from different patterns, they could be connected. Given a K-pattern network, a subgraph is a A1, A2, AK core if for each vertex in the S pattern, it is connected to at least AJ vertices from the Jth pattern, while A does not equal to J. For example, this is 3-pattern network. The first pattern contains vertices A1 and A2, while the second pair contains vertex B1, B2, and B3. The third pair contains vertices C1 and C2. It is easy to verify that vertices A1, A2, B2, C1, C2 form a 1-2-1 core. The A1, A2, AK core can be computed easily by following the peering-based paradigm. Now let me introduce the second group of models. This group may consist of two models that are focused on the vertices of the same type. Before introducing their definitions, let me introduce the definition of basic triangle and the circle triangle, which are also called B triangle and C triangle. We say that three vertices form a B triangle if each pair of them is connected by an instance of a metapath P. We say three vertices form a C triangle if each pair of them is connected by an instance of P, and the three metapasses form a circle. You can see that a C triangle is actually a B triangle, right? Let's see an example. This is a toy example with 6 researches and 5 papers, 1 venue, and 1 topic. By considering the metapaths APA, you will find that A4, A5, A6, these three authors form a B triangle, while the authors A2, A3, A4 forms a C triangle and also a B triangle. You can see that the three metapaths linked these three researches form a circle. Based on definition of B triangle and C triangle, the definitions of KP charts and the KPC charts are proposed. The first one is based on B triangle. It is the largest set of P pairs such that each P pair has a support of K minus 2 or more. Here, a P pair is a pair of vertices that can be linked by an instance of the metapath P. The B support of a P pair means the number of B triangles that a P pair participates in. Similarly, the KPC chart is the largest set of P pairs such that each P pair has a C support of K minus 2 or more. Here, the C support of a P pair is defined as the number of C triangles that contain the P pair. Let me show you an example. We consider the graph in last slide, and you can see that the 6 authors form a 3 B charts, while the left 4 authors form a C charts, or 3 C charts. So you can see that the 3 C charts is actually a subgraph of the 3 B charts. Okay, in this subgraph, each edge denotes a C pair. The B charts and the C charts can be computed easily by following the peering-based approach. The authors have also conducted a case study on the DBFT network using the application of community search. Specifically, let queryvertex be Zhuhan, who is a senior research, and K equals to 5. By using the B charts and C charts models, we can find 2 different communities. The first one consists of 2 groups of users that share 2 users, while the latter one is a clique. So you can see that the community of the C charts is more cohesive. Now let me introduce the third group of works, which are called clique-based models. First, let me introduce the concept of motif. Essentially, a motif is a small connected graph which follows HN schema. The motif itself is often meaningful and serves as the building blocks of large HNs. So here, example, this is an HN. You can see that there are some users and 2 companies and 2 colleges. So the schema of this HN is shown here. It means that the user can study in some college and work in some companies, and the users can also establish friendship with each other. And here is a motif describer, which describes that 2 users who studied in the same college and also worked in the same company. Based on the definition of motif, the motif clique is defined as follows. Given an HNG and a motif M, an induced subgraph G prime of G is a motif clique if G prime has the same set of labels same set of vertex types with the motif, and for each label-matched vertex set H in G', M is subgraph isomorphic to the subgraph of H. Let's see an example. So you can see that we consider the HN and the motif in the last slides. You can find that. For example, MIT, kite, Peter, April, these four vertices form a label-matched vertex set. It has the same set of labels with the motif, and the subgraph of them is also isomorphic to the motif. So this set, the subgraph of vertices in this set is a motif clique. And similarly, another one contains MIT, kite, Bob, and April, because these four vertices have the same set of labels with the motif, and the subgraph of these four vertices also isomorphic to the subgraph of the motif. Of course, the union of these two sets of vertices also form a motif clique. Based on the definitions of motif and motif clique, they also studied the problem of maximum motif clique enumeration, which aims to enumerate all the maximum motif cliques, which are M cliques but not containing any other larger M cliques. This problem is NP-hard. This is because even for traditional homogeneous graphs, the problem for enumerating all the maximum cliques is also NP-hard. So to solve these problems, it also follows the decay algorithm, which is a classical maximum clique enumeration algorithm, and then use backtracking to recursively search all the maximum cliques. Due to the time limitation, we ignore the details, which can be found from the paper. The clique-based cohesive subgraphs have also been extensively studied on k-party networks and multilayer networks. Given a k-party network and a k-party clique, which is also called KPC, is a subnetwork such that each pair of vertices is linked by an edge. For example, this is a three-party network. We can see that A1, B2, C1 form a 3PC because each pair of them is connected by an edge. And the subnetworks of A1, A2, B2, C1, C2 form the maximum 3PC because this is the largest 3PC, and for each pair of vertices from different partels, they are linked by an edge. On multilayer networks, one representative cohesive subgraph model is the multilayer quasi-clique. To introduce such definition, the gamma quasi-complete graph is first introduced. Given a homogeneous network and a value gamma in this interval, a gamma quasi-complete graph is a set S of vertices with degree gamma times S minus 1. Based on the gamma quasi-complete graph, the cross-graph quasi-clique is introduced. That is, given a multilayer network and a real values gamma 1, gamma 2, and gamma L, a set S of vertices is a cross-graph quasi-clique if in each layer the subgraph induced by S is a gamma I quasi-complete graph, and there is no proper subset of S has this property. Recently, some researchers have studied how to find the density subgraph on multilayer networks. To define the density subgraph problem on multilayer networks, first they need to introduce the definition of density. The most well-known density is called common density. That is, Given a multi-layer network and a subset of vertices, the common density of this set of vertices is defined as the minimum density on different layers. So you can see that it enumerates all the different layers, and for each layer it computes a density which is defined as the number of edges over the number of vertices. Based on the common density, the common density-based density subgraph is studied. However, this definition may be very sensitive to the noise, especially when there are some noise edges. To alleviate these issues, some researchers have proposed an improved version of this density, which is called a multi-layer density. That is, given a multi-layer network and a real value beta and a set of vertices, the multi-layer density of this set of vertices is defined as follows. So you can see there is a parameter beta which balances the importance of two different factors, which are the higher density and the number of layers achieving such a density. So you can see that the common density is actually a special case of the multi-layer density. Based on the multi-layer density, the multi-layer density subgraph has been studied. To find the density graph, the exact algorithms are often very costly, so researchers often try to develop the approximation algorithms by following the peering-based paradigms. That is, we first remove the vertices that are not likely to be in the subgraph, and during the removal process, we try to return the subgraph with highest density. The last model I would like to introduce is called the K-context structure, which assumes that the HN can be decomposed into one primary subgraph and several secondary subgraphs and some dipartite networks among them. So the K-context structure is essentially a set of vertices in the primary subgraph, such that for each pair of them, they are connected, while the secondary subgraph and the length of shortest path between them is not very large, and the total number of shortest paths between them is at least some value. Okay, that's all. Thank you.
Hi, I'm Wenjie Zhang from the University of New South Wales. In the following, I will cover the fourth part of the tutorial, related works, future works, and conclusions. Regarding related works, the following two topics are closely related to cohesive subgraph search or HANs, namely conventional cohesive subgraph models on homogeneous networks and heterogeneous information network clustering. Cohesive subgraph models on homogeneous networks have been extensively studied and many models have been proposed. Particularly, K-core model is defined regarding the minimum degree constraint, K-truss model regarding the strength of ties between two vertices. K-clique requires every pair of vertices in the subgraph to be connected. K-edge connected component model focuses on connectivity, and the densest subgraph model considers the density of the subgraph. For cohesive subgraph models on HANs, currently most of the existing models are extended from the cohesive subgraph models on homogeneous networks, and there also exist a few models which are defined by bringing new insights in other perspectives. K-core is a maximal subgraph in which each vertex has at least k neighbors in the subgraph. It is widely used in different problem settings to identify cohesive subgraphs due to the following important properties. First, it is fast and easy to compute. By iteratively peeling vertices not satisfying the degree constraint, the k-call can be computed in linear time regarding the graph size, and thus scalable to large graphs. K-call is especially useful in modeling the engagement of users in social networks, as the degree precisely captures the number of friends in the subgraph. The degeneracy of a graph is the largest case such that the k-call subgraph is not empty. It provides a good indication of the cohesiveness of the graph. K-trust is a maximal subgraph in which each edge is contained in k-2 triangles. It has some important properties such as each k-trust is a subgraph of a k-call. The edge connectivity of each k-trust is at least k-1, and the diameter of a k-trust is bounded by regarding the number of edges and the number of k. These properties directly follow from the definition of K-trust. K-clique is a set of k vertices of G such that each pair of vertices is connected by an edge. The K-clique is a complete graph with k vertices. It must be a subgraph of the K-trust, and it is also the most cohesive model among all the cohesive models on homogeneous networks. A k-edge connected component is a subgraph of G such that after removing any k-2 edges, the subgraph still remains connected. A k-edge connected component must be a subgraph of the k-call, and each connected component of the k-trust must be a subgraph of a particular k-edge connected component. This directly follows from the definition of k-call, k-trust, and k-edge connected component. The densest subgraph retrieves the subgraph with the highest density, where density is defined as the number of edges divided by the number of vertices. So after introducing the models of cohesive subgraphs on homogeneous networks, the next direction of related work is HN clustering. HN clustering aims to cluster all the vertices of the network into some sets, such that each set of vertices is densely connected internally. Compared with cohesive subgraph models on HNN, HN clustering is different in problem setting, criteria of defining cohesive subgraphs, and the general approaches. In terms of problem setting, cohesive subgraph search aims to search subgraphs satisfying the user's query requests, while HN clustering focuses on partitioning the entire HIN into a set of dense subgraphs such that each subgraph is weakly linked to others. Regarding the criteria for defining cohesive subgraphs are based on query parameters given by users. HN clustering, on the other hand, uses the same global criteria to partition the HIN. The general approaches are also different. Cohesive subgraph search solutions often work in an online manner, while HN clustering often based on some learning algorithms which are usually time-consuming and unscalable to large HINs. Next, I will very briefly introduce several works on HN clustering. The classic unipartite modularity is extended for bipartite networks and is computed as the accumulative deviation from the random expectation. The stochastic block model is applied for partitioning the bipartite networks based on the bipartite adjacency matrix. Another work on HN clustering utilizes the star schema to detect clusters with arbitrary number of taps and build a ranking-based generative model for each cluster. A social influence-based cluster method builds a social graph and an activity graph. Then, the social influence-based similarity is computed based on the social graph and activity graph. In the following, we will discuss the future work for cohesive subgraph search on HINs. The first line of future work is on the new models. As introduced in the tutorial, several cohesive subgraph models on HINs have been proposed, but they are still insufficient to cover all related real applications, especially for general HINs that contain various types of vertices and edges. Generally, there are three directions for studying novel cohesive subgraph models in HINs. The first direction is to extend the classic cohesive subgraph models that were developed for homogeneous networks. A potential research direction is to formulate new cohesive subgraph models based on the HIN connectivity and density, as these have not been comprehensively studied yet. The key challenge of the formulation is how to develop sound definitions of connectivity and density in HINs so that they benefit certain real applications. The second direction is to invent novel cohesive subgraph models like K-context. The third direction is to generate a new cohesive subgraph model by combining two or more existing cohesive subgraph models. This combination method has been studied extensively for homogeneous networks. For instance, we can combine the K-core and K-trace model together so that the result cohesive subgraph can maintain the properties of the two models. So in summary, there are various ways of formulating new cohesive subgraph models, but the feature of these models should be able to capture both the intensive link relationships among vertices and the type information of HINs. Another key challenge of cohesive subgraph search over big HINs is how to improve the efficiency to tame the huge data size and high computational complexity. Although existing works have made plenty of efforts to alleviate the issues of efficiency and scalability, there is still much room for further improving the search algorithms. To develop efficient algorithms, there are several potential research directions, such as to develop parallel algorithms to improve the efficiency, to develop index techniques to pre-organize the result subgraphs, and to develop approximate algorithms with approximation guarantees. An interesting future direction is to develop AI-powered cohesive subgraph search techniques. There are currently some initial studies on cohesive subgraph search over homogeneous graphs. In a recent study, the GNN model is applied to detect communities in the homogeneous network. So this problem has not been studied over HNN yet. In the models for cohesive subgraph search, often a parameter needs to be specified. The main challenges here are the different models have different parameters, and it is difficult to specify the proper values for these parameters. The future directions along this perspective may include automatic parameter suggestion based on statistics such as degrees, densities, and centrality, and to define an objective function to guide the search process. There are several online platforms for keeping large network datasets, such as Snap and LAW, which maintain a large number of network datasets to allow online users to download them easily. However, most of these networks are homogeneous networks, and only a few HN datasets are collected into these platforms. It would be very beneficial to build an online repository dedicated for HIN research to keep and maintain public datasets, source codes, papers, and prototype systems. As a conclusion, in this tutorial, first we make a classification of existing works according to the classic cohesiveness metrics such as call, trust, click, connectivity, and density. And then for each class, we review the representative models and solutions thoroughly. Second, we perform a thorough analysis and comparison of different cohesive subgraph models and their corresponding solutions on bipartite networks and other general HINs. Third, we offer a list of promising future research directions of cohesive subgraph search or HINs, which can provide researchers some good starting point to work in this area. As a summary, in the tutorial, we comprehensively reviewed the following works for bipartite networks and general HINs according to the models such as call, trust, click, connectivity, density, and other interesting models. Thank you for attending this tutorial, and we welcome questions from the audience.